Hi guys, in this video we are going to explore the shape of hydrogen orbitals. So this is the answer to the question that I've been promising throughout this mini series of lectures. We're going to be actually looking at a bunch of pictures and getting an intuitive feel for what atoms in general actually look like. And we're going to do this by focusing in on the so-called shape and size of hydrogen orbitals. All right, so that's our objective here. We want to figure out what these guys look like. Now remember, what we've done so far is basically motivated this concept of an orbital as a solution to the Schrodinger equation. We've said that there's an infinite number of these solutions, and each one of these individual solutions is characterized by a set of three quantum numbers, right? N, L, and M sub L. Okay. So our job now is going to be to look at essentially some pretty pictures to understand the form of these mathematical equations. And again, as I promised before, we're not going to go into any of the mathematical details. We're going to be presenting pictures that will illustrate the mathematical form of these functions geometrically. And then we're going to talk about the size of orbitals. And to discuss size, we're also going to be using a pictorial representation, but it's actually going to be a pictorial representation that explores the probabilistic aspect of these orbitals. So we'll talk more about that one at the end. First off, let's look at these set of pictures to understand what these orbitals look like. So first on, we remember we have four different types of orbitals that we've really focused on so far. We have those L equals 0 s orbitals, L equals 1 p orbitals, L equals 2, L equals 3 for the d and f orbitals. And one of the ways that we tried to understand and make sense of the relationships between these different quantum numbers was this little electron house analogy. And of course, that is simply an analogy. Using this little square house building up, a little square house allows us to keep track of the relationships between quantum numbers, count up total number of orbitals, and make sense of this labeling scheme. But of course, it does not map on to how these orbitals actually look in real life. So if we look at the mathematical form of an s orbital, right? So one of the s orbitals in that first little room right down there in the bottom left corner, these s orbitals are actually functions that have spherical symmetry. So they're illustrated right here. Basically, we have a mathematical function that represents a sphere for an s orbital. P orbitals get a little bit more interesting. So the three p orbitals that we observe right here, so we've got 1, 2, and 3 different p orbitals here. And remember, each one of those corresponds to the -1, 0, and +1 m sub L values. Each one of those orbitals has a relatively, unique form where it almost looks like what oftentimes folks refer to it as a dumbbell type shape, but a dumbbell without an actual handle in there, right? So basically two lobes connected together, at one point here in the middle. And the difference between the three are just their relative orientations in space. So to get an appreciation for what I'm talking about here with these p orbitals, again, we have three of them, a pz, px, and a py. Okay? Now notice, what I'm plotting here are the three different p orbitals, and the nucleus, right? Where that nucleus is situated is right there where all three of these axes come together. So that would be kind of our 0, 0, 0 point on our Cartesian grid. And these lobes for the pz orbital are oriented such that the z-axis is pointing straight out the top of this little dumbbell shape. The px is oriented such that the x-axis is pointing straight out the top of the dumbbell. And then, of course, similar to defined for the y. Okay? So we could spin these around in space, and we can see that all of these orbitals are identical. If I didn't have these axes labeled, I could just spin one around and then it would look like the other. Okay, so it's important to keep that in mind because that's going to have important consequences later on when we start talking about the relative energetics of these different orbitals. And so for right now, I want you to have this little dumbbell shape in mind whenever you see a p orbital. A little dumbbell with the nucleus centered right there in between those two lobes. All right, and then the d orbitals, shown here in green. These guys are even more interesting. So, like with the s orbital, there was only one sphere, right? When we had the p orbitals, we essentially had two spheres, two lobes kind of brought together to make a dumbbell. Now we've got a total of 4 lobes brought together when we're forming these various d orbitals. Right? And then there's also another structure where there's a dumbbell shape with what looks like a little donut coming around, the equatorial region where those two lobes are coming together. So if we flip over here to our interactive display, this orbital structure of the d orbitals can again be visualized. We can spin it around right there in the center where those two lobes are coming together. On the inside of that donut is where that nucleus is. And so we basically have an electron description, an orbital that has a probability density above and below this XY axis, and then a whole little donut of probability density right there around the center. Okay, so you're going to be able to find the electron anywhere in this region. Okay, and then similarly, if we flip through the different types of d orbitals, we of course have a total of 5 of them. And the difference is basically, just like we saw before with the p orbitals, their relative orientations, when compared to those Cartesian x, y, and z axes. And that's going to be the main orbitals that we're going to be seeing in this class. I'll just mention here, for the sake of completeness, that as you go to higher and higher quantum numbers, in this case we'll look at f orbitals with an L equals 3, you basically just get a more and more complicated lobe structure. So you start to see images like this where we have a total of 6 different lobes that are describing that electron distribution around the nucleus. And of course, the complexity grows with increasing quantum numbers. But like I said, most of what we're going to be focusing on for this first class in chemistry is just the s, p, and d orbitals. So it'll be very important that you're familiar with each one of these shapes. And I'd want you to be able to, for example, identify, given any one of these images here, identify that they are in fact d orbitals, and be able to distinguish them from the dumbbell shaped p orbitals, or of course the spherical s orbital. Okay, so now that we have a feel for the shape of these orbitals, let's now say a few words about orbital size. So to appreciate orbital size, we're going to have to go back to that definition that I presented a couple mini lectures ago, and it probably didn't even stick with you. So that's fine if you completely forgot it. It was a pretty abstract statement. Basically, what I told you is that these orbitals are mathematical functions that satisfy the Schrodinger equation. Hopefully you guys remember that. And these functions describe the wave-particle nature of electrons through a probability density. Okay, so if we're going to try and understand the size of orbitals, we're going to have to start paying attention to what it is meant by a probability density. All right, and once we do that, then we're going to be able to have a rather complete picture for the hydrogen atom. So we already have gone through all of our facts. We know there's an infinite number of these orbitals, okay? And we know that for each one of these orbitals, there's a corresponding probability distribution, and hence a corresponding size, okay? And that's what we're going to be looking at here. So when we come up with that combination of 3 integers, those 3 quantum numbers, and label a specific orbital, each one of those labeled orbitals will have a corresponding size, okay? We've already talked about the shape, okay? So let's jump on in there and try and understand how we can relate size to this concept of probability density. So it sounds a lot more complicated than what it is. I think one of the best ways to introduce a probability distribution function is a nice and simple example. So let's look at an apple tree analogy here, where we've got an apple tree that's been watered really nicely, and it's got plenty of sunlight, and it's producing a whole bunch of apples. and those apples are falling out of the tree when they become ripe, okay? And we'll just let them sit there on their ground. So if we've got a bunch of these apples sitting on the ground, and then we break up the area around the tree using a series of concentric circles, okay, illustrated here in black, we can then ask the question of how many apples are present in between any two concentric circles. Okay, so you can see right there at the tree trunk, there's no apples around it, so you're not going to have the number of apples right there at the tree trunk. Well, the tree trunk's in the way, so it's going to be 0. Okay, but there's a higher number of apples in that first concentric ring around that apple tree, so we then see a large spike in terms of the number of apples that you see in that first ring. Okay, so this will be like our first ring. If we then go out to our second ring, there's still a fair amount of apples, so we've got a fairly high point on that apple number that we're putting on the y-axis here. If we increase our distance of the trunk even further and say go to 3, well then the number of apples starts to diminish, and you go out to 4 and 5, and if you go way out here, and if I were to make a really big circle out here, well there's no apples out there, so it's going down to 0 as you go a long ways away from the trunk. So basically this is a little mathematical description down here that allows us to represent the number of apples at a given distance from the trunk. Okay, so once we have this nice little function here, we can fit it, and obviously we can get, if we go really skinny with our, the relative spacing between these different concentric circles, we can get a smoother and smoother function. And this function is going to provide an approximation to the probability of finding an apple at a given distance from the trunk. In other words, this little curve right here is exactly what I mean by a probability density. Okay, so not too bad. That is a probability density. But of course the question is, how does this relate to electrons? Well, remember that orbital solution to the Schrodinger equation are orbitals, each one of those orbitals, and we already know how to label the orbitals, we already know what they look like, right? With each one of these orbitals, there is a corresponding probability density that's given by the modulus squared of this wave function. Okay, so this probability density is the probability of finding an electron in that given region of space. Just like on the previous slide, we saw this was the probability of finding an apple within a given region of space. Okay, this probability density defined by the square of the orbital wave function is the probability of finding an electron in a given region of space. Okay, so here's where we're going to tie a number of concepts together. So electrons are behaving as both waves and particles. So if we ask the question, where is that electron located in space? Well, that is a very much a particle type question. Right? Remember, waves are spread out in space. They're all over the place, okay? And location is a characteristic of a particle. So if we're asking a particle question, where are you, Mr. Electron, then we're going to be getting a particle answer, okay? So if we have a, say, electron in a 1s orbital, okay, we remember those orbitals are spherically symmetric. So notice I could kind of draw a nice little sphere here. Okay, I'm going to put my nucleus right there in the middle. Okay, and I ask the question of that electron in a 1s orbital, where are you? Well, then I'm going to be getting a particle answer. And at some point in time, and I'll put it in blue here, I think I'll kind of point out, one little electron could show up right here. Okay, now if I take another hydrogen atom with an electron in a 1s orbital and ask the same question, then that electron's going to show up and say, hey, I'm right here. Another one's going to say, hey, I'm right here. Another one's going to say, here, I'm here, I'm here, right? And if we do this hundreds of times, thousands of times, then we are going to build up an image that looks like what I have on the screen here. So I'll clean it up so you can see it. So we've got a bunch of these blue dots, right? Each one of them corresponds to an electron answering that question of where are you? And each one of those answers are coming from an electron that was in a 1s hydrogen orbital. Okay, so identical systems, but we've got a whole bunch of them. So you've got, I don't know, it looks like maybe there's at least 1,000 dots here. So you've got 1,000 identically prepared hydrogen atoms, all of them with electrons in a 1s orbital. You're asking the question where the electron is, and we're building up this dot density that's telling us where each one of those electrons tells us that they are. Okay? And then what we can do, just like we saw with the apple tree, is build up some concentric circles and say, okay, well, how many of those electrons answered the question by saying, I'm here, and showed up in a given one of these concentric circles? And so if we do that, we are going to build up what is called a radial distribution function. Just like we saw for the apple tree, it turns out that there's a lot more electrons that are answering the question and saying, hey, I'm right here, and showing up in this little inner region here. So if I were to color in that inner region, that would correspond to, say, this region on that probability density. I can go with another color and say, okay, if I now include this region out here in red, well, that would be the next little sliver, okay? And you can see as you start going larger and larger in that distance from the nucleus, denoted here by R, right? So R is, you can kind of think of it as a radius, distance away from that nucleus. As this R gets higher and higher, we'll notice that the density of dots falls off, and it actually falls off exponentially, okay? So we're now able to capture and understand what's happening here and see how quantum mechanics naturally treats this wave-particle dual nature of electrons. There's a wave function, an orbital, that describes a probability of finding an electron in a given region of space. But when you actually ask the question, where are you, electron, you get a particle answer and you get a little dot, right? But the probability of finding that dot in a certain region is governed by this radial distribution function, the modulus squared of that wave function. So you might want to replay that part of the video again, because there's a number of subtleties there that are very important for understanding and really appreciating what these hydrogen orbitals are and what quantum mechanical orbitals are in general. Okay, so now I want to point out a couple other features of these wave functions before we move on. So when we're looking at this probability density, notice that this function here, as I said, it's exponentially decaying. Okay, but one of the characteristics of this exponential decay is that the function itself asymptotically approaches zero. Okay, so if you remember back to your math classes, what that means is that this radial distribution function, this probability density, is getting closer and closer to zero, but it's never quite zero. And so when you are looking at an electron in a hydrogen atom, a 1s orbital, right, you're going to obviously be most likely to find that electron, relatively close to the nucleus, right? But because each one of those electrons corresponding probability densities has a small but a finite value at an arbitrary distance r away from the nucleus, you could still have a chance of finding that electron quite literally anywhere in the case of this function. So if I have sitting here in the lecture hall, a hydrogen atom, and we ask the question, where are you, electron, there's a chance that that electron could show up at McDonald's down the street, or on the moon, or in an adjacent galaxy, right? Now, of course, with the exponential decay, the probability of such an event becomes vanishingly small very quick, but it is nevertheless something that could occur. And this is something that holds for all orbitals, right? So if we had a 1s orbital on the previous slide, if we look at a 2s or a 3s orbital, we see that at long distances, there is this asymptotic decay, okay? Now, the important thing to note here, as you go to these, different different quantum numbers, 1s, then we went to 2s, 3s, the shape of those probability distributions do change, okay? And one of the most striking features of these probability distributions are these regions where there is zero probability of finding an electron, okay? We call those nodes. And so the higher the principal quantum number of n, right, for a given L, the more nodes that you end up having. We saw that for a 1s orbital, right, there was effectively no nodes. You just saw something that looks like this. But when we put in, increase that principal quantum number by 1, we now see 1 node, and then 2 nodes when we increase it one more time. So what I'm saying here is that you could find the electron in this region, and this region, but never right here where these dashed lines are, okay? So you might be confused for a second there and say, well, hey, wait a minute. How is it that an electron can be here or here or here, but never right in the middle? How does it get from side to side? Well, remember, the electron is both a wave and a particle. So before you observe it, it's behaving like both. And so these nodes are a manifestation of that wave-like behavior. And you can think about this, that, if you were to tie a rope to the wall in one part and you were to maybe stand over here and, wave that rope up and down, there's obviously going to be a standing wave that's created in that rope, where you have, a changing amplitude of each one of those rope sections, but there's going to be regions in that rope where the amplitude does not change. Okay? And we actually call those nodes as well. So that term node, to describe this region where there is zero probability of finding an electron in our radial distribution function, is borrowing that terminology from wave behavior, because electrons are behaving as waves. Now, to draw out these concepts a bit further, the associated CDF interactive CDF interface will give you an opportunity to play around with these probability densities. So what I've done here is made a little program that allows you to select the desired value of the principal quantum number, n, right here, and we can change n to either 1, 2, 3, or 4. And then we can control the value of L. So let's keep L at 0, and we'll start off with n equals 1, which of course corresponds to a 1s orbital. Okay? And so what I'm plotting here is the probability density for a 1s orbital. Okay? So it's telling us the probability of finding that 1s electron in a given region of space. So if we start off way over here, distance from the nucleus, and there's a little slider control up here, okay? If we start off at a distance 0 from the nucleus, we're right at the nucleus. What we're basically saying is that the probability of finding that electron in the nucleus is 0, okay? Which better be the case, because if that electron goes into the nucleus, he's not coming out. There's that positive-negative attraction, and remember, this is one of our motivations for quantum theory. And now quantum theory is telling us, these solutions to the Schrodinger equation itself is telling us that electron's not going to crash into the nucleus. There's zero probability of finding it there. But as soon as you move any finite distance away from that nucleus, then there becomes a finite probability of finding that electron in that given region of space. So, for example, if I, say, move out a distance of 1.2 Bohr radii, which is a convenient unit of distance that you guys will be doing some practice problems with here in a bit. And so for right now, just take it as a unit of distance, and we say, hey, let's look at the probability of finding that electron at 1.2 Bohr radii away from that nucleus. Well, to determine that probability, we're just looking at the total area under the curve of this probability distribution function, which is an integral for those of you who've taken calculus. So the area under this curve up to 1.2, and it turns out that that corresponds to about 43% chance, which means if you are measuring the location of an electron, then 43% of the time you would expect to find that electron within a distance of 1.2 Bohr radii. And now notice, over here on the right-hand side of the interface, I am drawing a little sphere, a cross-section of a sphere that's illustrating the size of the region that we are examining. So this distance of 1.2 Bohr radii away corresponds to a sphere that is 1.2 Bohr radii in radius. And so if I increase the distance from the nucleus, that notice the size of that sphere is getting larger, and the probability of finding the electron in the corresponding region of space is getting higher. And we can see once we go out to about 5 Bohr radii, we're capturing 99.7% of the time you're going to find the electron in this region. Okay, but keep in mind that we have this asymptotic approach of 0, so we could, find that electron literally anywhere. Okay, so now I'm going to keep it at 5 Bohr radii, and we're going to look at the corresponding area under the curve here and say, okay, for a 1s orbital, 99.7% of the time, we're going to find that little electron in this region of space. Okay, so we've got our little setup here. And now what we're going to do is change the value of n. We're going to go to a higher value of n and see what happens. So I stayed right there at 5 Bohr radii. But what happened? When we were at a 1s orbital, we were guaranteed to find that electron in this region 99.7% of the time. But if I stay with that same 5 Bohr radii distance and I'm looking at a 2s electron, well then you're only going to find a 2s electron within that spherical shell roughly 35% of the time, right? And if you go up to a n equals 3, we're only going to find it there 9% of the time, and as you might predict, it'll be even smaller probability as we go up to the 4s, okay? So this is where we can talk about the concept of orbital size. Okay, so what we see as we go to these higher values of n is that the probability of finding an electron at a distance further from the nucleus is larger for larger values of n. So I'm going to say that one more time, and maybe you can go back through this video, right? When you are increasing the value of that principal quantum number n, you are increasing the probability of finding that electron at a larger distance away from the nucleus. So if we're way out here at, say, a 3s orbital, and we want to capture, 95% of, say, of the probability density, well, we're going to have to zoom way out, so far out that we're going to have to zoom out on our little, spherical shell monitor there, in order to get up there into that, 95% region. Okay. And similar things happen for, when we're looking at the number of nodes that we saw in the previous slides. Notice that for n equals 1, s orbital, 0 nodes, and we're looking at the radial distribution function. So we call these radial nodes. So we have 1 radial node when we get to n equals 2, 2 radial nodes at n equals 3, and 3 radial nodes when we get to n equals 4. All right, so if we go back here and we can do the same sort of thing looking at different types of orbitals, and we'll see that each one of these orbitals has their own corresponding radial distribution function, and hence the same sort of concept of size or region of high probability of finding the electron. Okay, and notice that once we went up to the p orbitals, right, the first p orbital, 2p orbital, we no longer have a radial node, but if we go to a 3p orbital, then we get 1 radial node. Okay, and you can play around with this interface, and I encourage you guys to do that and get a feel for the different values that the electron can take, or that the probability distribution of finding electron in a given region of space can take. All right, so to sum it all up here, the shape of atoms has now been as satisfactorily as we're going to be able to answered. Okay, electrons exist in these wave function orbitals that have a size that is defined probabilistically. Right? So what we typically do is draw atoms and draw these orbitals, and that's what I did on all those previous slides. When we drew a dumbbell-shaped orbital for a p orbital, put it right there, or a cloverleaf orbital for a d orbital, basically what I said was, hey, let's draw the region of space where we are, say, likely to find the electron 95% of the time. Okay, and if you look at all of these orbitals and you smash them all together, all the p orbitals, d orbitals, f orbitals, and go on from there, there's just more and more of these lobes, and you overlay them, you end up with something that looks like this, which the higher the number of orbitals you have, looks more and more like a sphere. So now we have quantum mechanical justification for representing atoms like we have been all along, by little spheres. But we want to remember that those spheres are not hard. They're mostly empty space. Remember that nucleus is very dense right there in the center. And those spheres surrounding that nucleus are regions of probability of finding the electron. Because the wave-like nature of electrons makes them inherently spread out in space. Okay, so that's our answer then. We now know what atoms and look like from a quantum mechanical perspective, and we're now going to move on to our final discussion, which is electron configuration. So we're now going to talk about how do we determine which one of these orbitals, which we now know the shape, size, and labels for, are occupied in a given atom.